This video is brought to you by SRA Soldering Products. Hey everybody, it's Jimmy from the DIY and Digital, and today we're building a Arduino-based current sensor from scratch. Welcome back everybody. Today we are following up on a previous tutorial where I talked about using current sensors for block detection and occupancy detection, and we used this little device. This is an NCE BD20, and what it basically is a Hall effect sensor that has been engineered and designed to be able to pick up the current differentials in model railroading, and it works amazingly well. It is very solid. I have yet to have it fail out on me, but the thing is, these things are about $20 to $25 a piece, and if you're looking to switch out a lot of them or add a lot of them to your railroad, that can get really pricey. So what I wanted to do was figure out how to build one myself. So I've done a lot of research and tried to figure out a way to do this that wasn't incredibly complex. So let's go ahead and dive into the build. Here are the parts you're going to need for this build. An Arduino, in this case I'm using an Arduino UNO for the prototype, a breadboard, 5 wires with male DuPont connectors, a 5 amp current transformer, 2 1 million ohm resistors, a 1N4148 diode, and a single LED. First, we're going to install our current transformer. Next, we place our resistors. We place these in series, connected to the right side of the current transformer if the black side of the current transformer is facing you. We then connect our diode to the same side. Now keep in mind that the diode has an anode and a cathode side. You'll want the cathode side closest to the current transformer. On this diode, it is the black side. We then place our LED. Now we hook up our wires. First, the LEDs ground and power. White is for ground and red is for power. We then add a white ground wire for the resistors. We then connect this yellow wire to the anode side of the diode. Finally, we take this black wire and connect it to the opposite side of the current transformer for our 5-volt power. Now for the Arduino connections. First, we take the black wire from the current transformer and hook it up to the 5-volt pin on the Arduino. We then take our yellow wire that's connected to the diode and connect it to pin A0. Then, our red wire comes from the LED's positive side to digital pin 7. A reminder that the positive side of an LED is the longer pin. And finally, we connect the 2 white ground wires to the ground pins on the Arduino for both the LED and the sensor itself. This next step is optional, but I like to do this in advance. The way the current transformer works is by having the wire that is going to the isolated rail wrapped around it a few times to be able to detect current. I like to pre-wrap some wire that I can attach to the bus line later for this. Now I typically get good results when I wrap this wire around the current transformer 4 times. And there's our setup. Alright guys, so that's how you do the build. Let's go ahead and jump into the code. Okay everyone, we are in our Arduino IDE, and the first thing we need to do is we need to declare our integers. Now we're going to do an integer a little different than we normally do for the first one. We're going to do long result. That's what we're calling it. And what this is basically, this allows us to store more data in the variable storage. So we need a few more digits for this. So what we're going to do is we're going to say that that is longer variable storage. Then we can do the rest of them as normal integers. So int num samples, and that is going to equal 10, and that is number of readings, and I'll let that make more sense here in a minute. Then we're going to do int clear count, and then that will be our clear test variable. And so that basically just tests out, that's telling us how many times has been read clear, and that's what it's going to be stored as. Then we need to do int clear sample, and that's going to equal 100, and that means that basically that's the number of clear samples are needed. We're going to do int threshold equals, and in this case I'm putting this number 550, but this is the number that is going to be your minimum sensor value before the whole system is tripped. So this is where you will adjust it rather than having to go to the code. I'm going to start coding my Arduino tutorials like this so that you can just go and adjust this number once rather than adjusting it in every single different state. So this is the minimum threshold. For tripping the sensor. And the last thing we're going to do is we're just going to have another integer that is value. And that's our final read result. So now we can start into our setup. So we'll go void setup, do our parentheses and our curly brackets. And then we do serial dot begin, that's a comma, dot period, begin, parentheses, 9600. And that starts our serial monitor. Then we're going to do pin mode 7 is an output, and this is just something that I've added on here. This will, when you put this into an actual application controlling lights, you will put all of your lights in here, but this is just an indicator LED for occupancy, just so we can see it rather than looking at the program itself. And that's it for what we have to do in the setup. So now we can do our enumerations. So we're going to do enumerate occupancy. Then I'll put my curly brackets. I'm going to do st underscore occupied, comma, and then st underscore clear, comma. And we'll put that right there, and we'll just say that these are our occupancy states. And then we need to do occupancy, and then occupancy, probably need to do some better syntax there, equals st underscore clear, and that is our default state. Now we can go into our loop, and this is where things are going to get a little more interesting here and versus what we've done in the past. So we're going to go ahead and do void loop, do our parentheses and our curly Q. And the first thing we need to do is we need to declare an integer for reading our A0 pin. So I'm going to do int, and I'm just going to do my standard one, which is value A1. And that equals analog read a 0. That reads our analog pin. So now we're going to do our math function for getting the average of what we're going to have for our readings. So basically what this is going to do is the raw readings coming out of the current transformer are very, very wild and all over the place. So we've taken a few pieces of circuitry and made them a little less wild. That's really what the diode does. It helps regulate it a little bit more. And then we do the rest of the regulating and reading through math functions. Basically, we're going to average out, in this case, 10 readings. That's what that num sample is. That's right here. We're going to take 10 readings, and we are going to put them together and average them out to get what our actual reading is. And this is done extremely fast in the program itself. But let's go ahead and start in on this. So the first thing we need to do is int result equals 0. Then we need to do a for statement, which is something we haven't done before. We're going to do int I, so that's a variable we're using, equals 0. Then we're going to do a semicolon. Then we're just going to have an I is less than, then we'll put our variable num samples. So that is our 10. So that's this number right here, the 10. So just think that's the 10. Don't look at it as something crazy. So we're saying for when I is less than 10, in this case, then we'll put another semicolon, and then we'll do plus plus I. And what that's going to do is it's just going to add numbers, continue. It's going to add the sensor readings together on and make I until we hit that num samples equals 10. So once I is, so it's going to be, right now I equals 0. Then you do, if it's less than 10, then you're going to add 1. I equals 1, I equals 2, I equals 3, I equals 4. Then we're going to do result plus equals value A1 divided by num samples. And basically, this entire function gives us an average reading over 10 readings. So when the current transformer is sending us things that are all over the place, this is going to give an average of that, and it gives us a good place to where we can set our threshold and all sorts of things like that. So because of that, we're going to put value equals result, and then we're going to do serial dot print ln value. All right, and then after all that, we can put a delay of 10, which is a reading every 0.01 seconds. All right, so now we need to do our switch. So we're going to start off by doing switch, and then we're going to do occupancy. Remember, that's our switch title. And actually, I need to put that in parentheses. Then we're going to do that, put the curly Q open. Then we need to do case st underscore occupied, put a colon, then we're going to do occupied, and then put value A1 in there, and then break. And that sets up our occupied state. Next we're going to do case st underscore clear. Then we're going to do, this is where it gets a little weird. I just have to do this for formatting. Clear 1. So as you can see, when I do clear, it's actually a function that goes on in the program. So I type in clear 1, and then I do the value A1, close that, and then break. And that sets up our clear state. So that is it for our loop. So now we can go into, we're going to do the clear one first since it's the simpler one. So we're going to do void clear 1 int value A1, then do our curly Q. First thing we're going to do is we're going to do clear count equals 0. And this resets our clear count. Next we're going to do digital write. Remember we set up that LED. So for pin 7 is low. Now if you were doing a signal thing, you would put all of your signal controls right there, right before we do this next line. So now we do if parentheses value is less than threshold, we're going to add in something that's going to make it a little bit easier to read. You don't have to do this. I'm going to do serial dot print ln parentheses quotations block is occupied, and then close that up with a quotation and a parenthesis, do our line, then we'll do occupancy equals st underscore occupied, and that switches us over to occupied. So that's it for the clear state. We don't want to do anything crazy because I actually want the clear state to be very sensitive, and even if it slightly misfires sometimes, it'll reset fairly quickly. But the clear state, pretty much anytime it goes below that threshold, it's going to flip to occupied. Now we want to do the opposite for the occupied state, so let's go ahead and start in on that. So we're going to do void occupied int value A1, and then we'll open up our curly Q bracket right there. Then the first thing we're going to do is digital write 7 high. And that turns on LED indicator. Next, we need to do our if-then statements for switching this back to clear. So we do if, we're going to do 2 parentheses, value is greater than threshold. Then we'll do our double ampersand for and. Then we'll do clear count. Remember, that's how many readings it takes to clear the block. Is less than clear sample, and that's how many it needs to read. So those numbers are the ones that are right here. So clear count is just the variable of how many have been taken, and clear sample is how many need to be cleared before it clears the block. So if the number of samples taken is less than the number of samples needed to clear, then it's not going to show clear. So we'll go ahead and open up another curly Q. Then we'll do clear count plus plus. And what that does is it adds 1 to the clear count. So every time it cycles through that, it's going to say 1 plus 1 plus 2 plus 3 plus 4. So eventually it'll count to 100 when it's perfectly clear. Now let's say it was a false clear. So the second thing we need to do is if value is less than threshold, and clear count is less than clear sample, clear count equals 0. First of all, we need to say that this adds that just adds to the clear count. This resets the clear count if a false reading was taken. And last but not least, we do if value is greater than threshold and clear count is greater than, now this is where we have to do something a little weird here, clear sample minus 1. The reason we do that is because if we just say clear sample, it does something weird there because it isn't going, it's going to stop right on that clear sample because of the if-thens. So we say clear sample minus 1. So when it hits that clear sample, it's automatically going to trigger this if-then statement. We'll put our curly cues. We'll say, we'll do our little add-on of the text, serial print, parentheses, quotations. Block is clear. And then we'll say occupancy equals st underscore clear. And that is it. Let's go ahead and check it and see if it works. Okay, it just had to correct a few typos there. I had an extra A in analog read, and then I had a colon instead of a semicolon there, so I had to fix that. But there we go. We can go ahead and upload this. This video is brought to you by SRA Soldering Products. SRA Soldering Products out of Massachusetts is a hard-working team that has made it their mission to be the premier supplier of soldering and brazing alloys. My favorite thing about them is they are more than a supplier. They want to help you get better at soldering. Everything from their easy-to-navigate website to their free How to Solder Electronics guide to their instructional YouTube channel is designed to help you. I've even been working with them to launch a soldering kit just for model railroaders, and you can check that out in the link in the description below. SRA Soldering Products, sra-solder.com. All right, so we've built it, we've coded it, we've loaded it. Let's check out the product. First thing we need to do is connect our sensor to the main bus using the wire that we pre-wrapped around the current transformer. Now we can power it on and run a train through. A reminder, this works through isolating a section of rail and using that as our detection zone. In this case, the detection zone is right here. You can see that our indicator LED pops on when the train is in the detection zone, even when it is not running and does not have any lights on. This is because even with all power off, it is still completing the circuit and allowing some current to flow through. and the motor acts as a resistor, which means that it's increasing the draw of current, which is detected by the current sensor we've made. You can also use rolling stock with metal wheel sets that have resistors on them. You can buy these pre-made and you can also make them. I've shown you how to do this in a previous tutorial that I'll link right up here, as well as in the description below. This one in particular has a 10K resistor on it. I do want to try it with some lower level resistors such as a 5.1K resistor, but you can see that this one works. The sensor is just a little less sensitive to this level of resistance. You can also see that if I bring the piece of rolling stock into the detection zone with a train and then detach the train and take the locomotive away, that the detection zone stays occupied according to the sensor until I go to take it away with a locomotive again. And there you have it, a DIY DCC current sensor. Alright guys, so that is an Arduino based DCC current sensor completely built from scratch. I really hope you guys enjoyed that. It's kind of a mix of half the components that make it work and half the code that makes it work. So a lot of research went into that, so thank you guys so much for watching. I want to say a big thank you to all of my patrons. They actually knew that I was building this way in advance because I was showing them on my Patreon page. So you can join my Patreon page for as little as $1 a month. Thank you guys so much for watching. Until next time, I'm Jimmy from the DIY and Digital. Stay safe, be kind, and happy railroading. There we go. That was the one. That was the one. Yes. There's a water heater back there making noise. Oh no, is that my washer? I don't know. This is a garage, so.